All right, the fundamental theorem of algebra. We're going to do the first part today, which is absolutely nothing new other than some vocabulary. So we're just going to practice some more of what we've been doing. But the fundamental theorem of algebra, you guys already know. It's the theory, we already know that the nth degree polynomial can have at most that many roots, meaning x to the fourth. How many real solutions could it possibly have? 4. We know it's going to have 4. They might be real, they might be imaginary. But at most, the number of solutions is the highest exponent that is in the polynomial, correct? All right, so the fundamental theorem of algebra talks about complex numbers involved in that as well. Complex numbers means the ones that have i's in them, right? You're going to use the fundamental theorem of algebra and obtain the linear factorization of a polynomial. All that means, guys, is the step before is how you answer. Meaning, if you come out with x equals 4, x equals 3i, and x equals negative 3i, right? Those are your 3 zeros. Those are the ones that we found. Your linear factorization is the step before you got x equals. It's our parentheses. So if I moved 4 over here, this would become what? X minus 4. If I moved 3i over here, it become what? X minus 3i. And if I moved negative 3i over here, it becomes what? X plus 3i. So all we're doing today is we're going to solve, and then we're going to talk about different ways these questions can be answered. They're going to ask you sometimes to write the the complete linear factorization. That would be this. They might say they want it irreducible over the reals. And you guys are like, what in the world does that mean? We'll talk about that in 1 second. So if you're finding the zeros of a polynomial, this is a first degree polynomial, yes? So how many answers are we going to have? 1. When I set this equal to 0, I have x minus 2 equals 0. So x equals 2. Everybody agree? Yeah? Okay. So here, set this equal to 0. How many answers am I going to have? 2. So this becomes what times what? Gives me a 9 when I multiply, but a negative 6 when I add. Minus 3 minus 3. So when I set both of these equal to 0, I get x equals 3. But how many solutions do I have? 2, because I have x minus 3 twice. What does that mean if I have the same answer twice? It's multiplicity. Good. All right, all stuff we've talked about. 2 times. So if we look at the third degree polynomial, if I'm going to find my zeros, how do I solve this? X cubed plus 4x equals 0. So what do? I'm going to factor out an x. Good, GCF. And I'm left with x squared plus 4 equals 0. Agreed? All right, how many answers do I have? I should have how many? 3. What can you tell me about one of them? And what can you tell me about the other 2? 1 is real. And 2 are what? Imaginary. How do I know by looking at this that 2 of them are imaginary? Because when I move the 4 over to solve, if you have x squared plus a number, that means you're going to have imaginary solutions. So if I go ahead and solve this, I have x equals 0. And here, when I set this equal to 0, I get x squared equals negative 4, right? So x equals plus minus what? 2i. Do I have any multiplicity or anything? No. Okay. What about this? How many answers? 5. I'm going to factor out an x cubed, and I'm left with x squared plus 9. I still have 5 answers. I got 3 on the outside, 2 on the inside. When I solve this, guys, if you have x cubed equals 0, if you take the cube root, you get x equals 0. How many times? 3 times. Good. Are they real? Yes. What's going to happen with x squared plus 9? What is it? Plus or minus 3i. Good. X equals plus minus 3i. If you were to tell me that that's x equals plus minus 3, I'd mark the whole thing wrong. there's a major difference, guys, major difference between an imaginary number and a real number. So we've got to pay attention to that. But does everyone see at different parts of the problem, you can already identify how many solutions you have and what kinds they're going to be. You understand? All right, so if we talk about different vocabulary, a quadratic factor with no real zeros is said to be prime, or what's called irreducible over the reals. You guys are like, what? What does it mean to reduce something? If you reduce your weight, what happens to it? You lessen it, right? What if you reduce a fraction? You simplify it. Irreducible means you can't break it down anymore. That makes sense, that word? Irreducible. And over the reals. They're talking about you get to a place where you cannot break this down anymore and get what kind of an answer? A real solution. Do you see how right here, x squared plus 1, I cannot break that down anymore and get a real answer. You guys need to be able to see that. There's going to be some questions that are going to ask you to factor where it's irreducible over the reals. That means if you can see, you know that your answer is going to be an imaginary, this is where you would stop. If it says the complete factorization, that means you can include the imaginaries or not. So nothing is different from a solving aspect. It's just how you answer the question and how it's asked. So I kept all this here just so you guys can see. I worked it out with first period, but I kind of left the explanations here so you could see it. So if it just says to factor, if it just says solve, do whatever you want. If it says to solve using the rational root theorem, then you have to use P over Q. If it says solve by the quadratic formula, you have to use the quadratic formula. But if it doesn't give you specific directions on how to solve, you guys can do anything. So if it factors or groups, do that. If not, then you have to use P over Q. But do you guys see in that first step, when you factor into two polynomials, what kind of an answer am I going to get here versus here? This is real, and this is going to be imaginary. How do I know that just by looking? Because when you move 5 over to the other side, -5, it becomes positive. When you move the 4 over to the other side, it becomes negative. And this happens because we're going to take the square root. So these two factors are irreducible over the rationals because you would get the square root of 5. That's not a rational number. It's a gross decimal. So you have to pay attention to what the directions are saying. If you can't break your answer down into a nice, pretty whole number that's real, then you can't do anything else. It's irreducible over the rationals. If it says you want something irreducible, leave it over the reals, that means, okay, as long as it's a real number, you're fine. If it's a silly, gross, radical or something like that, that's okay. But it just can't be what? Imaginary. Don't break it down anymore. And then if they want it completely factored, you break it down completely. So notice those three different things. Over the rationals means nice, pretty, whole, real numbers only. Irreducible over the reals means only real stuff, nothing imaginary. And then completely means break it all down. So that is that's what we're looking at today. We're not looking at the math part of it. We're looking about how they're telling you to answer the question. That's going to be very important. You guys have a quiz next Wednesday, and it's only over this section. So what we're doing today, and then what we're doing on Monday. We're going to practice on Tuesday, and then your last quiz of the quarter is on Wednesday. And we're going to do 2, 6, 2, 7 for like 4 or 5 days. It's like a lot of stuff, and we put the two sections together, and then we'll take a test over all of this stuff, and then 2, 6, 2, 7. So here is my suggestion. All right, here's my suggestion. I'm going to work these problems out, and then I think you should work backwards. Okay, because you have to pay attention to what the directions say. If it says over the rationals, then it's only pretty whole numbers. If it says over the reals, then you don't break down anything that is imaginary. If it says complete, then break it all down. So we're going to do all of them. Let's look at this first example. What would be the first thing? It doesn't say to use rational root theorem or anything like that. So if something groups or something can work out to factor to a trinomial to two binomials, do that. But what do I look at here? What's the first thing I can do? I can take out the GCF. Okay, I know I'm going to have 4 answers. So I know I'm going to bring out that x. And I have x cubed plus 3x squared minus 13x minus 15 equals 0. So I know one of my zeros is x equals 0. I would solve first because they're going to ask you for the zeros. And then look at the other way that they want the question answered, and you can kind of work backwards. I think that's the easiest thing to do. So let's just solve this like we normally would. I can't group this, right? Can I? So that means we have to use our P over Q. Let's list out the factors of 15. So plus minus 1, 2, 3, 5. I don't know why I put 2 either. After I looked at it, I'm like, what? Just kidding. 1, 3. That's why I'm looking at it. I'm like, why did I put that? 1, 3, 5, 15. Start with 1. Let's just see. As soon as we see something doesn't work, go ahead and skip. So I'm going from right here. So 1, 3, negative 13, and negative 15. So bring down your 1. 1 times 1 is 1. 3 plus 1 is 4. 4 times 1 is 4. This gives me negative. Is this going to work? Okay, so stop. Negative 1. Please. 1, 3, negative 13, negative 15. 1 times negative 1, negative 1. 3 and negative 1 is 2. 2 and negative 1, negative 2. Negative 13, negative 2. Yay! Negative 15 and negative 1. Woo! What did you guys just find out? X equals 1. All right, perfect. So I'm going to go over here and I'm going to say, okay, X equals 1. Good. Is it negative? Thanks. X equals negative 1. So now what do I do with what's left over? It's my resulting polynomial, right? X squared plus 2x minus 15 equals 0. Now you could just jump to the quadratic formula if you want to. But what should you look to do first? Look to see if you can factor it, guys. Can you factor this? Are there 2 factors of negative 15 that multiply to give you negative 15 but add to give you 2? What are they? X minus 3, x plus 5. So you have 2 more zeros here. One's at x equals 3 and one's at x equals negative 5. Everybody agree with me? So here they are. I got x equals 3 and x equals negative 5. Okay, what do you notice about all 4 of those answers? They're real. So you could write this as irreducible. The way that you would write your linear factorization, you can write complete over the reals, over the rationals, and complete because they're all real. So to write your complete linear factorization, it's the step before you got x equals. We've already done stuff like this. How do I go backwards? What would my polynomial, what do my parentheses look like if I'm going to go backwards? If I move 0 over here, it's x plus or minus what? Okay. I move negative 1 over here, it becomes what? X plus 1. I move 3 over here, it becomes x minus 3. I move negative 5 over here, it becomes x plus 5. That is your complete factorization. It's all linear. How do you know it's all factorization? We'll just go with it. How do you know that's all linear? What's the exponent on every single one of those binomials? 1, right? That would be irreducible over the rationals because all of those are rational real numbers. It would be irreducible over the reals because they're all real numbers. So you can write the whole complete factorization. You just have to pay attention to what the directions say. So if we look at the next one, all right, again, solve it. Solve first. It's easier to solve and then work backwards. If you solve first, look for a GCF. No. Can you group it? No. Ugh. So what do we have to do? P over Q. 1, 2, 4, 5. Where am I getting these numbers from? 10. Whoops, I forgot 8. 8, 10. What else? 20. What else? 40. Where am I getting these numbers? We're just making them up. Factors of what? 40. Of our last number. Good. P over Q. Rational root. So now I'm going to say, okay, let's try 1. As soon as something doesn't work, guys, move on to the next. 2 and 40. So bring down your 1. 1 times 1 is 1. Negative 7 and 1 is negative 6. Negative 6 and 1 is negative 6. 2 and negative 6. Is this going to work? Okay, just go on. Come on, negative 1. 1. Negative 7. 2 and 40. 1 times negative 1 is negative 1. Negative 7 and negative 1 is negative 8. Negative 8, negative 1. Is this going to work? Yeah. Let's try 2. 1, negative 7, 2, and 40. 1 times 2 is 2. Negative 7 and 2 is negative 5. Negative 5 and 2 is negative. Is this going to work? Should I just jump to something else? Or should I go methodically in order? I'd go methodically in order if you were me. So 1 times negative 2 is negative 2. Negative 7 and negative 2 is negative 9. Negative 9 and negative 2 is 18. 18 and 2 is 20. 20 times negative 2 is negative 40. What did you guys just show me? One of my zeros is x equals negative 2. Now with my resulting polynomial I have here, it's x squared minus 9x plus 20 equals 0. Factors of 20 that multiply to give me 20, but adds to give me a negative 4. What kind of 5, what kind of 4? X minus 5 and x minus 4. Good. So my other two solutions are 5 and 4. So x equals 5 and x equals 4. What do you notice about all three of those numbers? They're real. They're also nice, pretty whole numbers, right? So you can completely factor this over the reals, irreducible over the rationals, all that, because these are nice, pretty whole numbers that are real. So your complete factorization would look like what? X plus 2, x minus 5, and perfect, x minus 4. So on your quiz, you're going to be asked to find the zeros and then read what the directions say. It might say irreducible over the reals. That means if it's imaginary, don't break it down. It might say irreducible over the rationals. That means if it's not a nice, pretty whole number, don't break it down. Or it might say completely, and that means break it all down. So in a question like this, okay, a couple things you can do here. Some of you really like P over Q. It may be a little tedious, but you can kind of get through it. You can find stuff. That's totally fine. But the first thing I'm going to look for is there a GCF? No. There's 3 terms. So this is a trinomial. I have 3 terms. You can jump to P over Q. Factors of 6. Make sure you account for x cubed and for x to the first power with a 0. But can I factor this to where I have factors of 6 that add to give me 6? Multiply to give me 6, but add to give me 7? What would that be? 6 and 1. They're both positive. And then what do you notice about x to the 4th? What could I put in the front of each parenthesis? X squared. What do you guys notice about these 2 parentheses? They're not real. None of them are real. This is called what's a prime polynomial. You have 4 solutions, just none of them are real. So depending upon what the question asks you, all right, we're going to find the zeros. Let's go ahead and find the zeros. I know I can find what x equals. Do you guys agree with me that when I move the 1 over, I get x squared equals negative 1, correct? Let me do it. So if I move the 1 over, I get x squared equals negative 1. Then when I take the square root, I get x equals positive I and negative I. Do you guys agree? Okay, so on the right-hand side over here, I move 6 over. It becomes negative 6. I take the square root, so I get I root 6 and negative I root 6. Yes? Okay, so there's my 4 zeros. If the question said irreducible over the reals, this would be your answer. If you were to factor and leave your answer irreducible over the reals, that would be your answer. Because what happens when you factor completely? When you break it down, what happens to your answers? They become what? They're imaginary. So this, I'm going to say, is irreducible over the reals. That you can't go any further because everything is imaginary. Now, if they say they want it completely factored, you guys can do that. You're going to have 4 answers, so we're going to have 4 parentheses. This is our complete factorization. Complete. What does x equals I look like the step before it? When I move positive I to the other side, it becomes what? X minus I, good. What does x equals negative I look like the step before it? X plus I, good. What does x equals I root 6 look like the step before it? X minus I root 6. And then what does x equals negative I root 6 look like the step before it? X plus I root 6. I think your best bet, guys, is to solve first. Kind of survey your answers and say, okay, I have 2 imaginary, 2 real. Now let me look and see what it says. If it says to factor completely, complete linear factorization, that means you can have i's, you can have square roots in your answer. If it says over the rationals, that means they want just nice, pretty, real whole numbers. If it says over the reals, nothing is imaginary. Just got to pay attention to what the directions say. If you look at number 4, first thing we look for is a GCF. There isn't one. Don't automatically just go, oh, I got to do P over Q. Guys, can you group this? Yes. If it just says solve how you can. If it says solve using rational root, that means you have to do P over Q. Solve using this, you have to do. If it just says solve, see if this groups. It makes life easier. What can I take out of x cubed and 3x squared? X squared, and then I'm left with x minus 3. Agreed? What can I take out of negative 2x plus 6? Negative 2, and I'm left with x minus 3. Okay, so x minus 3 comes out in front. Yeah, that's our new GCF we write at one time. And then our leftovers get their own parentheses. So x squared minus 2 equals 0. What do you guys notice right now? It's going to be real. All of them are real. So if you're going to solve, let's solve first, and then we'll write all the different factorizations we can. If you're going to solve, do you guys agree with me? You get x equals... No, x equals 3, right? And here, when I move negative 2 over, it becomes positive. Take the square root, so you get x equals plus minus root 2. Everybody agree? All right, so we're going to write our 3 different kinds of factorizations. We're going to write irreducible over rationals. Then we're going to write irreducible over reals and complete. In this case, what 2 are going to be the same? Complete and reals, yep. So if I'm going to irreducible over the rationals, I can have x minus 3 and then x squared minus 2. Why do I leave the x squared minus 2? I don't break it down. And over the rationals, why do I leave x squared minus 2? So it's not a square root. It's not an irrational number. But over the reals and complete, in this case, are both going to be the same. Why are they both the same? Because they're real numbers. They may not be pretty, but they're real numbers. So my factorization would be x minus 3, which is great. And then x equals positive root 2 and x equals negative root 2. What does that look like when I put it back into a binomial? X what? X minus root 2 and x what? Plus root 2. Good. Very good. Let's just say, let me make up a say you factor and you get x equals, this is an example, this is not part of the one above it. Say you get x equals 4. No. Yes, I'm going to do that. X equals the square root, we'll say plus minus the square root of 7. And you get x equals plus minus 5i. Okay? We're going to write our factorizations. We're going to write all 3 of them. We're going to write over rationals. We're going to write over reals and complete. These are all going to be different, right? You guys agree? Okay. So if I'm going to write over the rationals, I'm only going to have one nice pretty parenthesis. This is going to be x what? X minus 4. What do these other 2 parentheses look like? How would I get x equals plus minus root 7? What would the parenthesis have to look like? X squared equals what? X squared what? Minus 7. Good. Remember, if there's a minus in between, when you move it over, that's okay. It's going to be positive. It's just going to be ugly. So what would the next parenthesis look like? X squared what? Plus 5. Perfect. Good. If you end up with a square root that is real, it's going to be x squared minus something. If you end up with a imaginary, then it's going to be x squared plus something. Yes, ma'am. No, because, oh, yes, because, okay, I see what you're saying. Because I didn't write that, right? Yeah. All right, we'll change it to that so it's a little easier to see. I understand what you're saying. Like, hold on. Yeah, we'll do it like that. So over the reals, what would I have? I still have x minus 4. That's fine. Then what would I have? Yep. So x plus the square root of 7, x minus the square root of 7. Do I do anything with x squared plus 5? Why not? Correct. What is my complete going to look like? X minus 4, then what? X plus root 7, x minus root 7, and then what? X plus I root 5, and x minus I root 5. Good. I think the easiest thing to do is find your zeros first and kind of assess the situation. Say, okay, which ones are real? Which ones are imaginary? Which ones are rational? Which ones are irrational? And then understand, over the rationals means all that I can break down is something that's going to have a nice, pretty, real whole number. Anything that would be irrational, which would be a square root you can't simplify, or an imaginary, you leave it in its parentheses. Over the reals means I can break down anything that's going to have a real answer to it, nothing with i's in it. And then complete means, oh, break it all down. Does that make sense? You guys okay? All right, the first part of your web